on to the next one, geometry. This one's 13-3, permutations and combinations. If you want to follow along in your book, it starts on page 836. Okay. So typically we start with these are key terms, and we define them. But this one we got to start a little differently. We got to take one step before that. We have to talk about what's called the fundamental counting principle. The fundamental counting principle says that if M event can happens M ways. Now this one, the first M event's a capital, the one's lowercase, and N event happens N ways. Well, that sounds a little like nonsense, but don't worry, it'll make sense. The total would be M times N. So for example, again, we all know that I don't have the greatest fashion, just an example. Let's say that I had 6 shirts, so I have 6 shirts I could pick from, and I had 4 pants. I have an M event, and I have an N event. And the total number of outfits I could make is 6 times 4, so I can get 24 total. Those are all the different combinations I could do. Now, like, I totally get that sometimes my tops can affect my bottoms, but we'll just pretend. So, moving on, let's go to an example. Using the fundamental counting principle, so example 1. Fundamental counting principle. Let's say we go to a sandwich shop and we can get different types of meals. So we could get, for our sandwiches, we could get ham and turkey. We could get salami. We could get tuna. We could get a club. We could get veggie. Or we could get meatball. And let's say we could have a side. We could get chips, fries, we could get a salad, or maybe they offer a baked potato. And then for a drink, we could get milk, water, tea, juice, or coffee. Okay. Let's say those are our options. Well, we could just physically map the whole way. We could go one path, 2 paths, 3 paths, and count them up all that way. That sounds like a pain in the butt. That's why the fundamental counting principle is so good. Instead of having to physically draw out the paths and count them, we just do our multiplication rules. Okay. So, how many different types of sandwiches could we get? 1, 2, 3, 4, 5, 6. How many different sides could we get? 1, 2, 3, 4. And how many different drinks can we have? 1, 2, 3, 4, 5. So, using the fundamental counting principle, we just multiply. So, 6 times 4, as I said, was 24, and 24 times 5 would be 120. So we have 120 options. Okay. So that's what the fundamental counting principle says. Now we're going to get into sort of the crux of the lesson. So first one we're going to talk about is called a permutation. A permutation is an arrangement of data and the big thing to remember is that order matters. Order matters. And often to do permutations, and as we'll get into combinations later, we do what's called a factorial. All my blacks are on the desk. A factorial. Factorial looks something like this. And exclamation point. The factorial is actually just the exclamation point. What it means is, so for example, if I have 6 factorial, that really just means 6 times 5 times 4 times 3 times 2 times 1. Factorial just means you multiply it by every number all the way down to and including 1. Now there's some weird different rules with it that I want to talk about factorial right now. 0 factorial is really, really strange. You would think it would just be 0 times whatever would be 0, right? Well, unfortunately, 0 factorial is always equal to 1. That's just how factorials work. So if you ever see 0 factorial is equal to 1. That's why we get 6 times 5 times 4 times 3 times 2 times 1. Technically times 0 factorial, which is 1. Okay. So we use factorials to find permutations. So on to example 2. Example 2 really shows how old this book is because it talks about something that you probably guys don't even do anymore. Let's say you downloaded 8 songs. And hit shuffle. How many different playlists are there? Okay. So remember when you hit shuffle, it just puts them all right in there, and then it just moves on to the thing. Now, we could write out like 8 different songs, and I could just do, let's say, song 1, song 2, song 3, song 4, song 5, song 6, song 7, and song 8. So I had 8 different songs, and I hit shuffle, and it's just going to switch up the order. The question is, how many different playlists are there? So let's think about it this way. How many different songs could be played first? 8. I could always start off with the first song played, which would be 8 to choose from. Now, let's say that was song 4 for our visual example. It doesn't have to be. How many songs can be chosen now for our second, in our second order? Well, that would just be the remaining songs, because you can't replay a song. So there are 7 other options. And then third, we would continue this pattern of 6. Fourth would be 5, and then we would get 4, 3, 2, and 1. Each of these individual song selections would be a separate event. So the fundamental counting principle says I would do what? Is I would have to actually multiply all of them. So I would get 8 times 7 times 6 times 5 times 4 times 3 times 2 times what? Or I would also get 8 factorial. Now I don't know if your calculators have a factorial button on there, but these do. So that's how it gets going, but you can always type out the long way. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 40,320 possible playlists. Now, if you want to get technical and say that each of those playlists is technically the same because it's the same songs, sure. But there's different orders we could have possibly had. So possible playlists or orders. Or, as a permutation is, just a different arrangement. Starting off a song with, starting off a playlist with a specific song versus ending with that song, completely different things. Because music is such a great thing. Now, we would just use a factorial if we're using every single one. Now, we're not always going to use all the same ones. What if I just wanted to pick 3 songs? Well, we actually get a formula for that. It's called permutation notation. And it's going to look a little goofy, but just bear with me. Permutation notation is little n, capital P, little r, equals n factorial over, parentheses, n minus r factorial. Okay. So let's break down what that all means. Okay. N is just the total I can select. Total options. R is selections. How many times I'm choosing. So that last example, I had 8 songs, I was picking 8 songs. Okay. Now the big thing to note is the factorial is outside the parentheses, so you would do the parentheses part first. So let's do an example and see how it works first before we start trying to analyze this formula. It's kind of goofy. So let's see. Example 3. Permutation notation. The environmental club. A club needs to select a president, vice president, and a secretary. There are 10 members. How many arrangements are there? Okay. So first we need to talk about, does order matter? If I was voted for the first position, would that change anything if I was voted for the third position or second position? And it would, because a president, a vice president, a secretary all have different rules and different things they need to do. So the order does matter. So again, I get my total, which is n, so I get 10, because NPR, and I get P. And how many positions am I filling? In this case, I'm filling 3. So I get 10P3, and that equals 10 factorial, because it's n factorial, over 10 minus 3 on the inside, factorial. Well, first, like I said, we need to do our parentheses. 10 minus 3, well, 10 minus 3, as you guys all know, is 7. So it's the same thing as 10 factorial over 7 factorial. Now you can definitely just type both these into your calculators and figure out what they are. However, the cool thing with division is some simplification can occur. So my highest number in the bottom is my denominator is 7. So I actually want to rewrite my 10 factorial. 10 factorial is the same thing as 10 times 9 times 8 times 7, and then I could keep going, right? Well, if this bottom is also 7 factorial, what can happen with these two 7 factorials? They can just be simplified out. So instead of doing 10 factorial, enter, divided by 7 factorial, enter, I can just do some logic there, so I know that my answer is going to be 10 times 9, which is 90, times 8, which would be 720. There are 720 different arrangements. And we could use the same fundamental counting principle from before. The fundamental counting principle said that how many different people could I choose for that first selection? I could choose 10. Well, after I've chosen somebody to be a president, how many people can I choose for that second position? I could choose 9. And then how many people can I choose for that third position? It would just be 8. And I would just multiply that. Because often if you're voted as the president, you're not also going to be the vice president or the secretary. That'd be weird collusion. I mean, for example, we obviously have President Trump and his vice president being Mike Pence. And then secretary, for that, there's a whole bunch of them. There's Secretary of Education, Defense, all that stuff. Okay. Now, we're going to get into something else. Now we've done permutation notation. Now we're going to do combination notation. Now the only difference, there's two differences. Well, obviously this is going to be a C. On the bottom you also have R factorial. That R factorial gets rid of a lot of different things. Now in a combination, order does not matter. All spots are equivalent. In a combination, order does not matter. So for example, if I were just randomly picking people to be up front during heads up 7-up, it doesn't matter if you're picked first or if you're picked 7th, you have the same position, same power. Order doesn't matter. Okay. So let's do an example. So example 4, combination. Let's say you're all college kids now, and you have to take some electives over the summer, just to help round out your degree. Now again, electives can be taken in any which order, so they have no influence over one another. Oh, I'm sorry, this one's a different problem. This one's about reading books over the summer. So, let's say you're going to read 4 books. And you have a list of 12. How many different combinations could you do? Now we're going to assume some important things. We're going to assume there's no series in there, because that order would matter. Obviously, if you read the 3rd Harry Potter, and then you read the 1st Harry Potter, that's going to be really weird and hard. We're going to pretend that they're all independent. But otherwise, they're not going to affect each other at all. So I would just use a combination. So again, n is my total, so 12 total books. And I'm going to pick 4. So I get 12 factorial over 12 minus 4 factorial, and then I would get 4 factorial. Okay. Well, again, we would always start with our parenthetical expression, so 12 minus 4. So I get 12 factorial up top, I get 8 factorial, 4 factorial. Now here, again, I want to look at my denominator and which term is bigger so I can cross off more. In this case, 8 factorial is going to be bigger. So just like earlier when I rewrote my top, I can rewrite my top here for combinations as well. So I can express this as 12 times 11 times 10 times 9 times 8, and I could keep going, but I'm going to stop there at 8 factorial, because that's our biggest term in the denominator, over 8 factorial, 4 factorial. Okay, now that I have 8 factorial in both, I can just do that, and now I get 12 times 11 times 10 times 9, which is way easier than typing out 12 factorial. So let's see, 12 times 11 times 10 times 9, 10,890. And 4 factorial, well let's see, 4 factorial would be what? 4 times 3 times 2 times 1, 24. And then I can just do 10,890 divided by 24. So there's, what? 12 times 11 times 10 times 9 divided by 24. Oh, divided by 24. 10,890 divided by 24. What the heck? I got a fraction, that's why I'm taking a second, sorry. have gotten 1089, I should have gotten divided by, okay, there we go. I shouldn't have gotten that one, I should have gotten 11,880. And divide that by 24, we get 495 different combinations. Yeah. See, even I get problems wrong every once in a while. Even I type something wrong in the calculator. It happens. But that's a good idea to know that you shouldn't ever get like a decimal value. You should always get whole numbers for combinations and permutations. Okay. Let's do another one. Okay, again, let's say you're a college student and there are 5 elective classes for you to take. Ooh, shoot. 5 electives. But you have room to, you can take 3. Now remember, they're electives, which means they don't influence one or the other, which means the order doesn't matter. Now what I mean by that is, if you were talking about, say, Algebra 1, Geometry, Algebra 2, it's been regulated that the order does matter. You're supposed to take them in that specific order. But if you're taking electives at college where you're just doing stuff all over the place, they're all intro classes, order doesn't matter. So in this case, it would be a combination. So 5c3 equals 5 factorial over 5 minus 3 factorial 3 factorial. Okay. Again, 5 minus 3 on the inside would give me 2 factorial. 5 factorial over 2 factorial, 3 factorial. Well, I can rewrite 5 as an expression to find my highest one. My highest one's going to be that 3 factorial, so 5 times 4 times 3. So I want to stop there. Over 2 factorial, 3 factorial. My 3 factorials are equivalent. So I get 5 times 4, which is 20. I get 2 factorial, 2 times 1, which would be 2. So there are 10 combinations. Okay, then I got one last example and that'll be it. This one's called Find Probability. So let's say there 3 pool balls are random selected. You should note that the pool balls are numbered 1 through 15. We are not doing the cue ball. Find the probability that the numbers selected are 5, 7, and 9. Okay. So find the probability if we randomly selected 3, that would be 5, 7, and 9. So, anytime we're finding probability, we want to find our favorable outcomes over our total outcome. So we want the probability that we select 5, 7, and 9 over the probability of the total. I want to use a different color for total just so we can keep it separate. Now if I'm randomly selecting 3 pool balls, how many different ways can I select 5, 7, and 9? Well, in this case, if I select 5, 7, and 9, or 9, 5, 7, or 7, 5, 9, etc., does it really change what I have? No. So the probability that I select 5, 7, and 9, well that one's pretty easy. The probability to select 5, 7, and 9 is 1. There's only one particular scenario where I select 3 pool balls and I get 5, 7, and 9. And that's when I get 5, 7, and 9. The big thing is I need to figure out my total. That's the thing at work here, is I'm finding my total. Now, does selecting one pool ball in any specific order affect anything else? If I selected the one right away, does that really affect my other ones? No, so this one would just be, again, a combination. So my combination is, again, how many total could I pick? 15. How many am I selecting? 3. And I get 15 factorial over 15 minus 3 factorial, 3 factorial. 15 minus 3, that's pretty easy, that's just 12. So I get 15 factorial over 12 factorial, 3 factorial. Now I want to rewrite my numerator in terms of where I stop at 12 factorial. 15 times 14 times 13 times 12 factorial over 12 factorial, 3 factorial. Then again, my 12 factorials can cross off. So I get 15 times 14 times 13. 15 times 14 times 13. 2730 over 3 factorial, which is 6. 3 times 2 times 1. So I get 455 total combos. And only one of those combinations is my 1579. So my probability of 579 would be 1 over my total, which is 455. As you can see with these combinations, just like with permutations, where if I really boil it down to it, I'm doing that factorial concept. Here again, I'm choosing 3, so I get my 15 times 14 times 13. And if it was just permutation, that'd be it. But what changes is the 3 factorial on the bottom. That's the difference. That helps me get rid of all my duplicates. This 3 factorial helps get rid of turns all of this into just one answer. That's why we have to include over the 3 factorial. Alright, that's all I got for you on this particular lesson. Thank you for listening and taking notes. I hope you guys have a great week.